Hi, this is Des Aubrey from Rarefied Technology Southeast Asia, or otherwise in short form RareTechSEA. Really just a video and a bit of background about who we are, who I am, you know, about heat transfer in general, and the kind of services that we offer to the industry. Just by a short way of background, you can get my website on raretechsea.com. In other words, let me spell that: RareTechSEA .odoo.com. We've been, running a bit of a temporary front end to the website here, and later on we'll refix our address. Just by way of background, I've been involved in heat transfer right from my university days. I was in South Africa. I started off in the practical sense, in those days what we call technical college, and I would spend 6 months on site, 6 months out at college in those days. And I actually worked for a construction company, and we built huge big paper machines for what was then Mondi paper in South Africa, and also SAPI as well. Monster machines. And it was an amazing experience. I met lots of people. It was a quite a leveling experience, because you're meeting folk from all over the world, and working there. And there were British folk and German folk and all kinds of folks. And then the actual people who were working on the machines, the fitters and so on, the artisans, they were all level of folk. And I learned to make a lot of friends, even though I was in those days, a white hat who was let's call it a young engineer in budding. And then I went over to a company called AECR. They took my bursary over and actually sent me to went to university after this construction company, and then that bursary was bought out by a big chemical company, and I worked with them for a while, and they offered me a very senior position, but I really had a passion for heat transfer. And so I also really wasn't too happy to move at that stage. So I decided to, in fact, join a small heat transfer company. And you're going to see me mention a little bit about these products. They were actually quite amazing. They are modular heat exchanger. It was a company called Transheat Pty Limited, located in South Africa. And the background to that technology is that there had been a Swiss-German inventor by the name of Gesalter. He was based in Panama, I think, at that stage, and he'd had some brilliant designs for the sugar industry, and they were basically built out of modules. And the idea is that you could take standard pipes and kind of put them together with machine components, and then using elastomeric seals to kind of rig them all together. And then he had a special spiral baffle, which in fact it's unique, and it forces the flow to go around the shell in a spiral pattern. In other words, you avoid the dead spots in general that you'd see in the typical type shallot tube, with cut baffles and so on. Or he was single segmented and so on. So it was very different, very novel, and I kind of fell in love with the idea. So I actually went to work with him for a while, and then that particular venture, I wrote their software. I did all the development of the software for them, and so the design process became very easy. I was put on a project. In those days, the mining companies were wanting to go into what we call the elution process, where they were recovering, let's call it the lost tails of gold, from let's call the mining dumps, literally. And they'd pump it through the process, and they'd eventually extract the last little bit out. And they had a special process for doing this. And they needed, at that stage, there were 3 heat exchangers. There was going to be let's call it a heater, to heat up going into the elution column, and then when it returned, a cooler. But we could actually put an intercooler in between interchanges. So we ended up with a combination which was then going to be entry into the interchanger, then goes out and through a heater, tops it up, goes through the column, comes back, passes the heat back to the intercooler, and off out through a cooler. But I did an analysis on it, and I realized we didn't need a cooler at all. We could actually drop one of the exchanges, bring the capital costs down, and push everything through the intercooler as well as the heater, as a trim heater. So it ended up being very cost effective. I later did a study on that, and you'll see it. I've got it on my Patreon site. You can see that study if you want to have a look at it, buy it. But it really is a 30-year review on how that concept worked. And they actually made a lot of money for this little company. But eventually I moved on because there were, career prospects were a bit tight in a small company, and that made promises that they didn't keep. So I then moved on back into, let's call it the product development, project development and installation at a company called Foster Wheeler. And then from there, I went out as a consultant on my own. And that's taken me all over the world. I ended up ultimately consulting and heat transfer. Because what actually happened is I was brought in and out of consulting sometimes to come and work for a company permanently, and then I'd go back consulting again. And at one stage I was technology director for 4 companies for a heat transfer group in South Africa. And that got me involved in a special process for brazing aluminium components. Very, very thin. We're talking about the stuff for radiators, automotive heat transfer devices that are very, very thin. We're talking micron level products, and brazing some of these is really, really tricky. And brazing aluminium has its downsides. There were 2 major processes at that stage: the vacuum process, and then there was also the what we call knock-a-lock process. And knock-a-lock, you have a clad layer typically on the tubes, and in many other cases on the fins, but it depends on the product that you're making. And then you pass it through a furnace, and eventually it melts this clad layer, and you bond the 2 materials together. But very tricky. Your time inside that furnace is very, very tricky. So this taught me a lot about how these furnaces worked. And so we had this process where we actually had aluminium particles that were coated with what we call aluminium eutectic particles, which have the right amount of aluminium and silicon to get the lowest melt point, temperature-wise. It's called the eutectic. And then this was coated with a flux particle, which is a unique process, and we call this the composite deposition process. And it was invented by a chap out in Llanelli in Wales. So that was a fascinating process. But we were the pioneers for it. When I came in, I was brought in as a technology director. So I took over this project as one of my portfolios. And this project had been through a nightmare. They'd had like 5.5 years of development. They'd poured a lot of money into machines, and nothing was really happening. And so I came in, and we just gave us a good go. I built a super team, really some fantastic young guys. And we kind of got this thing licked in less than 3 months, and really along the way reinvented. We challenged everything, and then we applied all the latest production principles, and we got this process stable. And it was actually made for commercial product. It actually went into pickup vehicles in South Africa. So it was a very successful product. But then once I'd reached that goal, I'd set myself to get this thing stable, I got a bit bored. And then I actually was made an offer, consulted sort of to talk to chaps in Sweden who were trying to do a similar process for copper and brass. And they'd been going a long time too, 8.5 years. So I said to them, right, give me a break. Let me come in for 3 months. I'll take it on risk. And if I can help turn your process in 3 months, then you keep me on as a consultant. So long story short, this project took me all over the world. I've been through 36 plus countries in my engineering career, all over. Okay. And we turned the thing. We turned it in less than 3 months. This had me kind of as the global jet setter. I would spend something like 80% of my month in an aeroplane. People would say, well, where do you live? I'd say, I'll seat aeroplane somewhere in the world. And I was traveling at one stage almost around the world every month. It was quite a story. But we were successful. So if you look on the screen, you'll see my cursor going over a product. This is what it would vaguely look like. I'll go through this one in a bit more detail later. But the process that we did for the Swedish company was called Cupra Brace. And it was a case of having brass tubes, special brass tubes, and special fins. The fins were copper, but they were anneal resistant, meaning that when you apply temperature to things like copper, they get to a point where they get soft. And sometimes that softening temperature is just too low, and they stay soft, So this company was called Outokumpu Copper Strip AB in Västerås in Sweden. They had developed a process that the moment you applied heat to this, in fact, you got a migration of certain particles in the fin. There was a bit of chrome in there. and basically that would then stiffen the fin. So after brazing, the fin was actually stiff, and you would sing, after brazing. So it was quite an amazing process, and I kind of loved this. I had a lot of fun, and we actually made success of it. We went up into the commercialization phase, and that eventually saw me in Siberia for 3 months in Russia in the middle of winter. That was quite an experience. But again, I kind of had reached what I felt. I'm a pinch hitter, typically a troubleshooter. So I'd kind of reached the end of where I thought I should be going on that project. So I then decided to move on. Typical me. And then I went back on my own again. I'm driven typically by challenges, invention challenges, design challenges. This is my bent. And so I went back on my own again. And at that stage, I had moved out to Thailand, because Thailand had become what they call the Detroit of Asia. They wanted to be developing vehicles in Asia. And so I came out here as a consultant for a while and kind of fell in love with the place, with Southeast Asia. The climate's nice. It's very nice and warm, and the people are nice too. So I did some extra research. I did a part-time PhD at their engineering faculty, and my topic was the wave nature of the Navier-Stokes equations. In other words, what is turbulence? What causes turbulence in fluid flow? So I've done a lot of research in that, and I've actually then at the tail end, I did all the coursework for it, and then eventually I've moved on into personal research. I run a whole lot of servers here, and I've actually been writing academic papers, and I've been around on academic conferences and chaired sessions and so on. So in India they call me professor for whatever that means. And then, what happened was we were in Asia for a while, and then went back to South Africa, took my wife back to go and visit. My wife is from Laos. Took her back to go and visit my folks for a few years before we came back here again. And while I was there, there was a manufacturer who'd made a special multi-port copper tube, fully copper. And it wasn't anneal resistant. This was just pure copper, So there was obviously going to be the challenge of, when you braze it, not to soften it. Well, soften it too much, so you didn't leave it in a permanent soft condition. And so what I did is put a project together for them where I brought in these anneal-resistant fins from Sweden, and I had a special brazing process which I developed. It was different, actually, to Cooper braze. And then we successfully trialed it, and you'll actually see that's a sample. If you look on the screen here now, that's a sample, in fact, coming out of the braze process. And we we had a lot of fun brazing, where we had nothing to braze with except a lamp furnace. So essentially, I had a South African friend of mine who's a real expert. He's really, really good on commercializing stuff, and a can-do guy. And he'd worked with me before as a director at TNN. And so we put together two, let's call it casserole dishes, stainless steel casserole dishes, as a protective environment. And then we pumped nitrogen through it, which is a controlled atmosphere brazing. And then we put the sample in the center. We set he designed the fixturing in that for me to get it to stay together. So that, during the braze process, it's quite critical that you hold it together properly, otherwise you get bad joints, all right? Because as you braze, the actual product starts to swell, expand because of heat. And what happens is, once you hit the braze point, everything melts and starts to hold it together. But the trouble is, once you then start to cool it, if you're not careful, you get gaps. We call it splits. So you have to have fixtures that keep it together nicely. And we did that, actually. We had a lot of success. It was really nice. It was cool. But and even managed to, because of the braze cycle that I developed for that process, we were able to do it without softening the copper tube. So that was a lot of fun. And so that's the kind of thing I do. And then I moved on to developing special compact heat pumps. I wanted to do this for the South African market, because what they do is have a geyser, what they call a geyser, which is a horizontal vessel sitting up in the roof. And typically they've got this insertion, heater in the electrical thing, and this thing really uses a lot of electricity. And South Africa, it was getting expensive, and also Eskom, who's the electrical supplier for the country, was actually running out of energy. So what I then did is I developed these heat pumps. I developed a 1, 2, 3, and 4 kilowatt range. And then we brought them to South Africa and put them through trials, the 1s and the 2s, and they actually became very popular during that time. So that was the kind of thing that I do, and I'll talk you through a little bit now. Well, before I get there, then after that I brought my wife back to Asia. We're out here in Vientiane in Laos. It's the capital city of Laos, and I'm kind of semi-retired. What happened is I was helping a company during COVID, and their let's call it their COVID prevention techniques and their testing wasn't that good, and I ended up in a high, let's call it viral load environment during the time of Delta, and I ended up with a very, very severe dose of Delta, and it really knocked me flat. It almost killed me. I ended up with Delta, then going on to long COVID, severe long COVID. I was paralyzed for like 9 months, and my legs really, I mean, it was more like a Guillain-Barré type syndrome, and it was nasty. And I wasn't sure if I'd make it again, but I was in hospital for three times, nearly died. But came out of that, and I'm very grateful to be alive. And so I've been rebuilding again, and rebuilding everything and picking it all up again. And so the idea really has been, I've put together a website, showcasing some of the technology that I've done over the years and what I'm capable of doing. And kind of, we were saying, doing the impossible in real time, miracles might take a little bit longer. And I say that not trying to be irreverent, but some things really do require a different brain. And I've been blessed with a slightly different brain, and I'm very grateful for that. So what I'll do now is walk you through a little bit about what you might see in our website, and if you find it interesting, that's fine. I really am. I can take on a range of stuff when it comes to heat transfer. I'm passionate about it. It's been my life's passion, if you want to call it that, right from university days. When I was at university, the typical classic course was to go into thermodynamics, but thermodynamics is an endpoint to endpoint process, whereas heat transfer was only hit that first year, and we had a heat transfer course, and I fell in love with it because it's the dynamics of the flow of energy. All right, and and what always got me is that the equations involved in fluids, in other words, getting the heat, let's say, out of a fluid and through a tube wall and so on, and going to another fluid, it's quite challenging. So between this kind of heat transfer and then, in other words, which led to heat exchangers, and then also leading to heat pumps, where you've now got you're pumping a lower grade energy upwards, is my game, and I love it. So let me just walk you through a little bit. Hopefully everybody can see. This is the website, and I've given you the details of the address, but let me just page through a little bit. So Rarefied Technology, Southeast Asia. We've provided advanced thermofluid technologies for almost 40 years. So things like technical consulting services, advanced technical software, thermofluid courses. We'll go into a little bit later about how to design. A lot of people have no real clue. People think that you just take a piece of software and you whack it out and you get an answer. And the trouble is you actually don't. Invariably, you don't get the best design out of that at all. So this is part of what I want to do, is to be able to teach people how it all works, and keep ourselves alive. Because of COVID, I can't really travel very much. I'm mobile, but I can't travel not like I used to. I used to travel all over the world, but it's not possible at this stage. And I've reached an age where I'm having to be careful. So anyway, it's a little bit of background. Let's just walk through it. So if you want to get hold of us, just contact us. Just click on that, and then there's a form you can put in whatever you like, or you can just email directly, and then talk here about changing the world of thermofluid technologies is possible. I don't take anything as impossible. We've done it before many times, and literally many times. And then so we welcome your inquiries. Please contact us. And so our details are at the bottom here, des.raretech@gmail.com. You can follow us. We've got a Twitter account, Facebook, and this is the Patreon account. You can contact us here at Patreon as well. I've got a lot of articles there on Patreon. You can join up free, actually, if you like. You don't have to pay. If you want to pay, I can offer you a lot of other detailed stuff that you won't get just on the free membership. But a lot of the posts I put up are free. So you can go through that and have a bit of fun. And home and about us tells us about who we are. And then, so walking through, let's go to the technology side. technology overview. What are the main things that we're involved with? Things like thermofluid technologies. Okay, this is actually showing something from this original shell side spiral baffle bundle. It's quite unique, and it's quite a trick arrangement. So, but again, with this there's a few idiosyncrasies that can improve this bundle as well. So things like what can we offer on the thermofluid tech side? Heat exchanger design, that's plate heat exchangers, which effectively, a lot of plate exchangers, there's very little information out there, but I'll give you a bit of background a bit later how I got what I got. Shell and tube, the traditional shell and tube, I can design that too, right through to refinery stuff. I've got the software for that. A little bit of background on that is, in my early years, one of the first of my own exchanges that I designed was a bitumen heater. It was actually designed to heat bitumen using thermal oil, and in fact, because bitumen's very difficult, it's non-linear. There's a huge change in viscosity. It comes in, it's like thick treacly stuff, and it comes out thinner than water out of the same exchanger. Now, to model that's really tricky. So I developed some techniques and technologies in my early years on that. So bitumen heaters, I've had a lot of success with those. And then modular shell and tube, I'll talk through those as well, perhaps in another video in a lot more detail, because they're fascinating. You can start from a single module and you can make a massive thing by just lacing them together. Okay. I've also done, in the bitumen heaters that I made, I did a similar principle, but I used high temperature stuff, because the thermal oil is up to 370 degrees C. And then things like automotive heat exchangers. Here the trick in automotive is that the fins that we use in things like, let's call it radiators and condensers and some evaporators, they're really trick. They're corrugated fins and they have louvers in them. And then to get the flow to move in and out, it's quite an art form. And even to be able to get a very high performance out of that. At one stage, I consulted to a company in Thailand, and we got down to very high accuracy on pressure drop and heat transfer. I had some software, and then I tweaked it actually to end up with some very, very high performances. We were talking heat transfers within the range of less than 3% out prediction, and pressure drop 5 to 8%, where most people can't get closer than 30% on on pressure drops in that. So we got very close. Radiators, condensers, evaporators, charge air coolers, things like oil coolers, plenty of that. And then air gas or coolers and heaters. Here you're talking about extended fins, lots of work in that area. I run a program here, and what we do for clients typically is we adjust for them their own, what their preferred, let's call it tube pitches are, and the fin pitches, and we actually set up a data bank for them, and then actually do designs, and in fact, if necessary, even give them software and say, right, you go ahead and then just send it to me for checking. So we can do that kind of thing. We can help you along a little bit on that. We don't have to be greedy. As long as you're fair to us, we'll help you. All right. And then steam air heaters, block fin. Block fin was a crowd in South Africa that was doing this quite successfully. I think it was designed, the machines were designed in the UK, and then these guys were doing this in South Africa. Quite nice. And then I introduced them to the idea of modular heaters and coolers. We actually can pack these, let's call it panels of heaters together or coolers, and do different things with it by just being a little bit smart. And then heat exchanger applications, landfill gas coolers, and I'll talk about it a bit later. I'll show you a picture of a real high-end landfill gas cooler. I was very proud of it. It was the first time in the world. And we had low pressure. What was happening is you take this landfill gas, which is methane and carbon dioxide mix, and with a lot of rubbish in it, and then a lot of water vapor too. And then that was then being taken to engines directly. And then those engines were fouling up. The engines would then drive the generators, which would produce about 6 megawatt, I think they were working on. And the trouble is the spark plugs on those engines would foul like every day or so. So what we did is we designed this low pressure. We had very limited space too, so that was a little bit difficult to do. I only had 50 pascals pressure drop allowance, which is like nothing. You can't even blow like that. And essentially that unit was able to capture a lot of the water and the crud, the rubbish coming through, and in fact acted as a wash down. We actually, the water that would come down as you cooled, we'd capture that and send it out. So you actually were dewatering and also catching a lot of the junk, and then every so often they'd open up and clean it off. So the spark plugs then they could run for months. It was quite amazing just putting that in. But that was a challenge. Remember, you're trying to put a gas over a fin, and there's no software that does that very nicely. So you had to do a lot of trickery to get that to work. And I spoke about bitumen thermal oil heaters, block fin heaters and coolers. I spoke about block fin, the special type of fin. You get the other type, of course, which is where you have these rolled-on fins as well. But the block fin's not bad. It's quite a high performance. Plate heat exchangers, lots of different applications with that, and you'll see later on we'll talk about the software side with the plates, and then modular shell and tube exchangers. Again, all kinds of exotic stuff there. And then optimized heat pumps, air to water. That was my little passion, these modular units that I designed. Things like liquid to liquid, air to air, gas to gas. The nano heat pump range I spoke about, 1 to 4 kilowatt. Micro heat pumps, man, you can make a heat pump that'll fit in your hand. So I have all that know-how and experience, and also how to remap gases on compressors and all that to do different performance envelopes. And then things like thermoelectric heat pumps, I've been toying in that area. The technology is not quite there yet for the lift that I'm looking for. With if you're doing domestic water, I want to get your water up to 60, 65 degrees C, and thermoelectrics are not quite there yet. They're for lower levels, they're not bad, And then specialized machines. This is where a lot of this came out of the work I did with the automotive heat transfer. Specialized machines like fin machines. They really are quite tricky. Corrugated fin machines, offset fin machines, flat fins, all of that, the kind of machines that actually make these fins. And then tube machines, folded tube machines, we call them B-tube. There's all kinds of variants on that. And then welded tube machines, where they actually take strip and they fold it and they weld the one end of it. B-tube, as I spoke about, you get different forms of the B-tube where you make a shape, you curl them over, and then when it goes through the brazing process, it seals up. Tricky. Complex folded geometries, I've got quite a few tricks here where I can integrate a lot of my know-how into special tubes here. Assembly machines, core builders, how you actually, now see I've got an offset here. Core builders, how you actually assemble things, how you put fins and tubes together. Complex hybrid machines, all kinds of mixtures I've designed. I was involved with this CD process I spoke about in South Africa, where we actually applied these flux-coated particles. We had to put it onto a glue, actually, which then went onto the aluminium tube to form this particle-clad layer. And we designed a special machine that was doing basically 50 tubes per second, a very high-speed type setup. To coat as well as dry and everything. And then slurry application machines. Also some tricks here, actually. I had some guys put together some very nice ideas for us, which surprised a lot of people, I think. So this is an idea of a direct coupled, what we call an air blast unit. So you'd have a fan, typically either blowing or sucking. Blowing's better. Sucking, you can tend to get cavitation back here if you're not careful. So blowing is actually better. What's critical with these things, of course, is the pressure drop. If you allow the pressure drop, if you don't match the fan properly with the fin profile, you can actually end up where the air doesn't go through the core properly. It all just spins over here and doesn't go through. It stalls. So you've got to know what you're doing. So the designer has to know how to couple the fan. At least get the spec right with the fan manufacturer, but also be careful. I've seen people overdo it, so they pump the motor too high and then nothing comes through the fins because the pressure drop through the fin is too high. It stalls. These are another kind of units. Again, you'd see the coming in and then you'd see it going out. So this is in all likelihood a steam unit. This is an oil cooler, and this is an interesting modular unit, which was a big fellow actually. It was put together and then sent up to Southwest Africa, and that's Namibia, And this is another idea of these modular units where you actually lace them together. Typically what you're going to find is these are 4 banks and it's actually coupled in series. So these modules are in series. You can imagine it's a really, really long exchanger by the time you get to the end of it. And then what's happened is I'm involved in software for plate heat exchangers. There's quite a history to that. I'll talk it through a little bit, we've got time. And that I acquired through a Swedish colleague, software. Shame that he's now passed on, but he was a guy who used to work with, let's call it a big name company, and they did all their original software development, and then they moved on eventually to form a company called SWEP, which is a well-known name today. And so that know-how, they continued with that know-how, and then built a small company and had software written and so on. And then eventually I helped them a lot, and then eventually I acquired the software, the rights to the software, and have improved it over the years and made it a lot more, let's call it, user-friendly. And it has a lot of tricks to this. Built into the software is a way to actually predict, given geometry, to predict performance, heat transfer performance and pressure drop performance of various plate geometries. So typically we use this as a baseline, and then from that I tweak a bit further if I've got experimental data or if I've got other software to compare against and cross-check. So I can actually tweak and get the software very accurate. I'm looking for high accuracy, where other software out there might get you to 15%. I want to be down in the 2 to 3% range. So accuracy, okay. And then so if you go and have a look up under we call it RTCalc, and there's various. At the moment we've released RTCalc Lite Designer 2024. And that I think is really reasonably priced. It's a starter kit, if you want to call it that, and it has a range of plates. But of course, we can create bespoke versions, which allow a user to say, "Hey, I want to add in extra plates. I want to add this, this, and this." We've got a monster plate library. I'll take you through that as well. So this is this RTCalc. It's lovely. I've actually put a lot of work in to make it very nice, and it's really come out as a concerted effort, but with well-known technology. Now, let me tell you something. The engine there that we use, the heat transfer engine and pressure drop engine, has actually been used by all the big names. What happened is this company also the big companies, and I'm talking big names, I won't mention names here, they'll be angry with me, but they would come to this little company and say, "Hey, we like your heat transfer engine, we're going to build a different interface, but we want to use your engine to do our calculations." So I can promise you virtually every big name that's out there that make plate heat exchangers, OEMs, actually use this engine for their software. Hidden at the back is the engine, the same engine that we use. All right, for this, but we've got a few more tricks in there. So just to give you an overview, and you can go in and you can open these up a little bit, have a look. Standard examples. So there's a whole list of stuff here on the left when you open it up, and you can see standard examples, there's design examples, there's a whole range of stuff. There's over 284 unique examples in this. And if you look at what's involved, you've got, single phase, you've got condensing, we've got evaporating, a pressure drop predictor for a certain channeled flowing liquids, and a batch. Where you have a batch process, the problem is, how do you design or select the right temperatures and flow rates for the let's call it the fluid, the primary fluid. How do you set it up for the heat exchanger? And that's where batch kicks in. It helps you to understand that, to get your parameters right. Okay. On how to get that batch process down. So here's an example of this is single phase unit, and you have all the input. This is the entry screen. So what would happen is you go and you click on single phase, boop, and it would open up with this screen. Okay, and then when you do the calculation, once you put in all the parameters, and if you look at the instruction manual, we talk about setting at least, you have to have 5 parameters to get a heat balance. If you put 4, it's not going to do it. If you put 6, it's also not going to do it. That's over-specified. So 4 is under-specified, 5 is perfect, 6 is over-specified. So you're only going to do 5. And we talk a little bit about that in the manual. And then so in this case here, what you'll do is you'll select the channel type that you want, and then you'll go ahead and calculate. And what will come out is, at the top is, let's say, your optimum unit, all right? And under that, second optimum, third optimum. In some cases, what we do on the professional version, we've got the light version and the professional version. Professional version we'll open up where you can actually do a full scan across a range, and we can set an optimum range like Alpha Laval or SWEP or something like that, and it'll do an optimum for you and select the right or the best exchanger for that job. But at the moment in RTCalc Lite, you can experiment with that in the SWEP option. We do allow that. So you then calculate, you get the exchanges that we're predicting. This gives you the screen output here, gives you the property outputs of the fluids and so on, and then you kick out into the reporting. reporting. Actually, what's also interesting further up here, you can select extended reporting over here if you wanted to, which allows a lot of extra parameters to come up, which is these things here at the bottom. So this will give you a rundown of the exchange that you're looking at, and for instance, design duty, physical properties, design heat exchanger, extra parameters, and so on. And then I'll go through just the last bit here. I'll go through the rest of the website some other time. It'll get a bit long otherwise, I think. So, novel brazing. This is something too. I alluded to this early on when I spoke about brazing of copper and copper. And here, this is quite trick. And you've really got to understand that if you're not careful with copper, temperature and duration, you will anneal the copper. And then the stuff's soft, man. So the final product is useless. If you take an aluminium radiator, okay, let's call it done with knock-a-lock, and you cut the header plates off, all right? And then you start to try and roll that radiator up. You can do it very easily. We call it the Swiss roll test. And you roll it up and you see if the fins break away from the tubes. Now, copper's the same. If you're not careful, if you don't manage the copper properly, you're going to get a similar problem because the copper gets soft. So the trick is to use these anneal-resistant fins, which don't actually go hard. I mean, there's no way you can roll that thing up. You can't even bend it. They're that tough, really. I remember when I was in Pittsburgh, we were doing brazing trials, and we had a Russian team come out, and there was a very strong guy. And he was trying to bend this stuff. He couldn't bend it. Couldn't bend it at all. So this became very popular, the Cooper braze in Russia. So yeah, so experts in novel particle braze technology, that's my game. I know how it works, I know the dynamics. So for aluminium, Cooper braze for copper, brass, and then we've got this novel process for ultra-thin copper products. We've got to be careful there. And extensive experience in the designing and tuning of cab furnaces, that's controlled atmosphere brazing for automotive applications. Things like radiation furnaces, convection, hybrid, which is a mixture radiation convection, semi-batch, batch operations. Inert gas and actually active hydrogen as well. I've worked with that. On the furnace side, I've actually consulted 2 companies on furnace design, batch furnace design, semi-batch, indexing furnaces, how to control the atmosphere, especially when you've got burn off. In some processes we have a binder, binding particles to a surface, and you've got to get rid of that. And if you don't get rid of that, you get carbon, because all these binders have got carbon in them. And the carbon stays behind, and it then stops, it de-wets. It causes de-wetting on the actual materials that you're working with. So you've got to be very, very careful. So brazing technologies, yes, composite deposition, things like aluminium foils, and I'm talking micron level foils. So aluminium silicon, or American aluminum silicon, powder coated particles, this is composite deposition. Cooper braze, this was the copper brass foils. They had the particle there was copper nickel tin phosphorus, which had a eutectic caused by the tin to give it a low melting point relative to the materials themselves. And the phosphorus there was a scavenger, but it'll only scavenge for so long, and after that you start to actually you kill, you poison the particles, and they don't braze properly at all. So you've really got to know what you're doing when you work with these processes. And then specialized brazing furnaces, so automotive brazing, for instance radiation, which was the classic radiation from the side or the tops. How do we do that? Convection, then you've got combined or hybrids, radiation convection. Binder burn-off control is exceptionally important. If you've got binders in there, you don't want to carry them into the braze zone, because if you carry them into the braze zone, it gives you de-wetting, as I said, and off-color product. So you have to be able to manage that carefully, and I've got a few tricks here that actually I've integrated with furnaces over the years, and it works. And then batch furnaces, how to get them to do what they're supposed to do. It's not always so easy. Again, composite deposition, Cooper braze, plate heat exchange has been involved there also with these vacuum batch furnaces. I've walked into somewhere, I've seen furnaces that are green because the guys got their atmospheric control wrong. So gas control technology, cooling systems, that's very important. You've got a coolant jacket at the end of it, and this thing's long, it's most of the furnace. So what they do is they put in, for instance, gas blast portions and even air blast at the end, obviously the final stages. But you can really shorten the furnace by being smart, Brazing cycle optimization, this is absolutely critical. So aluminium is critical because you've got a very small distance between the eutectic point at which you get the eutectic to melt and the overall softening temperature of the aluminium that you're trying to braze. Very careful, because you've got to build those cycles in a very, very careful, slow, gradual movement into the actual braze temperature. Whereas with copper and brass, we have got a very different cycle. I can go in here fairly hard and then pull where I need to pull and drop it out, so I keep the braze time controlled, and it's a very different cycle to knock. And also copper is very different as well. You have to be quite careful. So atmospheric types have been involved in control atmosphere, things like nitrogen plus hydrogen. You've got to be careful, because if you go over 8%, it can become explosive. And so when I used to do trials in these furnaces, I would have a 12-pack of hydrogen next to me, and I'd chase everybody away, and I'd do the runs through the furnace and just make sure that you don't stand at either end, because if hydrogen blows, it blows the ends out. So you've got to be very careful. So, and then just some pictures of the one trial we did in South Africa. What would happen is you'd do the run, it would come out, literally, you'd come out, the actual box that we had around it was glowing, literally, as we take it out the furnace. And to get temperature control, tricky. And I got the furnace right. And then I'd actually take it up and put it under a microscope and inspect the joints. And then what we're looking for is joint integrity. So if you look over here, the joint profile, because whenever you remember, when you've got copper's a funny thing. If you braze copper and you've got, depending on the alloy that you're using here, you can end up forming a bronze. And bronze has a lower heat transfer, thermal conductivity than the actual copper itself. So you've got to be quite careful what you do down here. And so that joint itself has to be critical. You don't want a big thick joint like this, because you get very little or very poor heat transfer. So again, there's a lot of know-how that comes into this. So I'll kind of call it quits there for today. And it's more of a challenge for me to get used to talking with the screencasting and so on. So that's a bit of an overview about technology. Next time what I'll do is I'll go more into detail on, for instance, RT-Calc, what's involved there. I'll probably put a whole session together on that, and then also to talk about our gallery. We've got a lot of trick stuff in there as well, which you might find very interesting. Modular shell and tube, extended fin, copper brazing technologies and braze products, and copper fluid dynamics, computational fluid dynamics. There are update with some of the runs that I've done over time, showing different configurations of fins and tubes and so on, and show you what actually happens to the flow. And then the last bit is the company itself, who we are, this good Patreon shop. If you want to buy our software and that, or buy a license to our software, you can get it through our shop. At the moment we're doing it through Patreon, because Patreon can actually pay us through Interlau, where some of the other providers can't actually do that. So Patreon opened a shop, and it seems to serve our purposes quite nicely. And then we've got news and a blog, and there's my resume. You can find a bit more about me, and I'll talk about those in more detail later, and about us. All right, so that's the basics of Rarefied Technologies. Thanks for bearing with me. I've been just giving a bit of background into how it all works out, and I'll say goodbye for now. Bye-bye.